All right, let's do problem number 3 on the constant velocity graph worksheet number 1. And let's read it. It said a cyclist's position along a straight line, a straight road, is described by an equation x equals 2.7 meters per second times time plus 2.0 meters. A, draw a position versus time graph from 0 to 10 seconds. B, draw a velocity versus time graph from 0 to 10 seconds. C, what is the cyclist's displacement from 4 to 8 seconds? And D, at what time will the cyclist be at x equals 9 meters? Use your graph and use algebra. Okay, so let's do all that. Now, I already set it up here with given, find, and solve. So given, x equals 2.7, as I said. And then what do we want to know? A, the position versus time graph for 0 to 10 seconds. Then the velocity, and then delta x for t equals 4 to 8 seconds. And then the time when x equals 9 meters. And you can use a graph and you can use algebra. I want to see both. So let's solve this. I'm going to zoom out a little bit, make room. So let's solve. Okay, well, let's position versus time for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8, 10. You can skip like that, make it a little faster. And you got to have the variable, and you got to have the units. And the increments have to be evenly spread out. Now, this is a little harder. How do I increment this? Well, 10 seconds, what's my distance at 10 seconds? Well, 2.7 times 10 is 27 plus 2 is 29. So pretty close to 30. So I'm going to go 5, 10, 15, 20, 25, 30. 10, 20, 30. And this is velocity in meters per second. Some of you are forgetting to put the units with your variable name. So always put the variable, or you could write out velocity, the whole word velocity, and put how you're measuring it. Okay, now to graph this, well, at t equals 0, this is at 2. So if this is 5, 2 would be right about there. And then at 10 seconds, it's at 29. Well, this is 25, so 29 is right here. And now all I have to do is connect these two. Now I notice that some of you are putting dots every second, and it'll work, but it's just more time than you need to do that for a linear equation. Does that make sense, how I did that? A little shortcut. Then it says for part B, it says velocity versus time graph. Well, we know that the slope of this graph here is our velocity, and the slope is right there, 2.7 meters per second. So this is pretty easy. And doggone it, I'm sorry. I'm not, and by the way, I misspeak all the time. It's just a bad habit. Well, not a bad habit, it's just, this is position in meters. Now, I was testing you to see whether you would catch me with that, and you all failed. So I don't know how you're going to live with yourselves. All right, so this is velocity in meters per second. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is going to be 1, 2, 3, and then the velocity is 2.7. And it's 2.7 the whole time, so the graph's going to look like that. So this is A, and this is part B. Okay? And see how I drew them one on top of the other like that? It's a kinematic stack. Now part C, delta x for t equals 4 to 8 seconds. So delta x equals the final minus the initial. Well, the final is at 8 seconds. So we'll say x equals 2.7 meters per second times 8 seconds plus 2 meters. And when you do that, I actually worked it out. You get 23.6, is that right? Meters, just off screen. Okay. So that's x final. And then x initial, well, it's the same thing, 2.7 meters per second times 4 seconds plus 2 meters. And when you do that, you get what? 12.8 meters. And when you subtract the final minus the initial, you get 10.8 meters. Now, another way you could do that is you could use this graph. Here's 4 and 8. So this is just 4 seconds. Oh, and I left this off, time in seconds. So I would have lost half a point if I hadn't caught that. So from 4 to 8 seconds is 4 seconds. So the area underneath this is also equal to that 10.8 meters. So you can use this graph or you can use that. And so delta x equals 10.8 meters. And then for part D, the time when x equals 9 meters. So, well, we just start off with our equation here, but we put in 9 meters there. So 9 meters equals 2.7 meters per second times time plus 2.0 meters. So I want to solve for time, so I'm going to subtract 2 meters from both sides. And I get 7 meters equals 2.7 meters per second times time. And then I divide both sides by 2.7, and I get time equals 7 meters divided by 2.7 meters per second. And when you do that, let's see, what do you get? See, 7 divided by 2.7. If you round it up, you get 2.59. And some of you rounded up to 2.6. I think that was fine. Now, also, let's take a look at the units here. Remember, this is a compound fraction. This is meters. I'll put it over 1. And this is, then you reciprocate and multiply. Right? This is a compound fraction, so you take the denominator fraction and you flip it over and multiply. So the meters cancel and you end up with seconds. So that's kind of cool. Okay, and there's, let me zoom out so you can see the whole thing. And I apologize for, I'm sure if you're watching this on video, you were kind of freaking out when I labeled that velocity, but you know, this 7th period class didn't catch it in time, so you know, you should always blame other people if you get a chance, you know, for your own mistakes. Okay, all right, life lesson. Okay, no questions? That'll work? Okay, that is all.